to week 7. In this week, we will start focusing on a very interesting use case that's very closely associated with big data, which is called as the streaming data use case. This use case is actually the counterpart to the batch processing examples that we've seen in the previous weeks, where we spoke about Spark, ETL patterns. We spoke about different types of transformations and actions that Spark is good at, and how you can code up some of those ETL using Spark. So those are all typically batch examples, meaning the data is getting processed once in a period. The period could be anywhere from a few hours or a day or a week, etc. Whereas in the world of streaming, the kind of data that we're talking about is not just large, but it's also very high velocity, which means that you cannot really keep buffering or storing data for long periods of time, because the data becomes very large in size very quickly. But more importantly, the usefulness of that data diminishes over a period of time, and it kind of diminishes very rapidly the moment the time of creation of the data is passed. Right? So there are lots of such examples in the real world. Like for instance, in our own daily lives, we consume news daily, right? From newspapers, from channels, TV channels, radio channels. The value of the news is actually very short-lived, especially for the most part the current affairs kinds of news. And that short-lived nature means that the faster you can get access to that news, the more informed you are. But if you get access to the news like 1 week down the line, it's already become stale, right? The usefulness is kind of zero at that particular point in time, because like the next day's news or the news 2 days later has superseded the value of the news that was created like a week ago. So that's the use case for streaming. A lot of different applications. We'll take a look at that. In this week's lectures, we will also start taking a look at what are the options available in terms of technologies in, let's say, one of the public cloud platforms like Google Cloud. I've picked Google Cloud only as an example, and especially with respect to streaming, they've got a point of view which is quite interesting, as opposed to the other methods which are typically open source, Kafka and Spark streaming based, which we will take a look at in the next week, in week 8. But for this week, we'll actually spend a bit of time looking at the GCP products, which are basically helping in the streaming processing. All right. So, what is the motivation? There are a few very big data cases which are extremely, critical in terms of time latency associated with solving or processing the data. And the moment you have that kind of a requirement, then streaming is like the first thing that you should think about. Streaming differs significantly from batch, and we will take a look at why that's the case. But from a perspective of use cases, you will see that a lot of these use cases look common, right? Look typical, and you might not even know that there is actually quite a bit of streaming related pipelining that's actually going on behind the scenes. But because these are two different engineering disciplines within data, it's important that you know to distinguish what's a use case which is purely batch, what is a use case which is more conducive for streaming. So let's take some examples. We've taken lots of examples throughout the various weeks of courses so far. So we'll continue to pick on those examples as well as some new ones. So let's take an example of IRCTC. We have taken a look at that scenario, business scenario, multiple times. Processing payments when you book a ticket is an example of a streaming application. So here, the data streaming is not of high velocity, but the data is of high concurrency, meaning multiple different ticket bookings happen at the same time, multiple different payments need to be processed at roughly the same time, and the payment processing has to happen instantaneously, which means you cannot wait for the payment confirmation to be released, because if you do that, then the use case becomes much harder to reason about. Like, was the ticket really paid? Have I booked my reservation or not? Can I give the confirmation to the customer without having collected the payment successfully? Will the customer defraud me if I don't collect the payment up front? Lots of scenarios that affect both sides of the equation. But if you're able to guarantee that the payment is processed instantaneously in real time, and that triggers the appropriate downstream workflows, which process the data and make the reservations, make the bookings in your booking system, then all of that constitutes basically a streaming application. Financial transactions, yeah, of course, a lot of financial transactions are real-time in nature. So, for instance, if you've seen the utilization of a credit card or a debit card, you might actually see that there are checks and balances that the bank has, which track where all you're using your credit card and bank or debit card. And if you use the card in a way that is abnormal, then you might get a call or an SMS, right? And you might have to, affirm to the bank which issues the card that you are still holding the card, you're still the genuine owner, the card is not stolen, the card is not with somebody else, etc. So it happens, for instance, if you try to pay at a point of sale and you use the wrong OTP or you use the wrong PIN, and then almost instantaneously, almost any bank in India will give you a call and say, hey, we noticed that your transaction was declined because of wrong PIN. Are you sure that you still have access to the card? Right? So that's an example of a streaming application where real time is of essence. So both these examples are point-in-time event-driven examples. There are other kinds of examples which are, continuous. Like, for instance, tracking and monitoring cars. That's a classic example. We've all been, beneficiaries of this when we take Ola or Uber, right? Like, for instance, in both those apps and maybe potentially other apps as well, you can share the location, and you can even share the ride with your family members or your friends, and they can, in real time, take a look at where you are. And it's not just about processing an event or processing a payment, it's continuously monitoring, right? What is happening with that particular asset, in this case, the car in which you are riding. So that continuous monitoring requires you to continuously deal with newer and newer data elements that have been streaming through. And it's a great example of where, if you miss a couple of events, if you miss a couple of status updates or location updates from that car, from the Uber, then it doesn't make sense to catch up to it, because already next event has come in. The next event has already updated the car to be at a particular place. At that particular point in time, it makes no sense for you to go back and look at the events that you missed, because it's stale, right? The data becomes stale almost instantaneously. So it's a great example of data streaming, how real time is a critical aspect, and how it's a continuous monitoring that you do, continuous event processing that you're supposed to be doing here. Another example of this continuous event processing or data processing is video, right? Almost all of us have seen OTT apps. When we download videos or we see movies, we see TV series, we get access to that data, and the data is continuous, right? So much so that if you end up buffering for, let's say, a couple of minutes because your internet connection runs, then at that time, it makes no sense for your application to go back and try to play that video again or play that particular segment again, because we've already moved on to the next segment. And this is especially true with live videos. Like, for instance, you're watching a cricket match live, or you're watching a football World Cup live, etc., etc. So that is an example again of continuous monitoring, where the data becomes stale very, very quickly. The third example here is interesting from a perspective of data processing in real time and in a way that's streaming. So this is the world of IoT. IoT meaning Internet Internet of Things. It refers to those devices which have had some kind of a data connection attached to it, like an Ethernet port or a wireless connection that allows it to transmit data. And that's what makes it smart, right? The smart refrigerators, smart microwaves, smart washing machines. The smartness comes from the fact that they have an IP address effectively, right? Or they have a MAC address, and you can interact with it remotely through software. And the way you interact is going to be personalized to the data that's being collected, the current scenario, the current climate in which the particular device is running. So those are all variations, but in effect, IoT devices are continuously producing data. And when they continuously produce data, the data is usually sensor data, then you need to be able to act on that firstly, and the same considerations of continuous monitoring of the assets also apply here. Like if you miss a couple of sensor data readings, it makes no sense trying to go back and stitch it because newer sensor data readings are already available. So you can't just catch up, right? You just have to keep abreast with the latest data that's coming in. But what's even more interesting here in these kinds of scenarios is not just the data collection, but to be able to do something with it, right? So here, when you look at, this is as opposed to, let's say, video processing, right? Where what you're really doing is just catching up to the latest time period of the video, so that you keep abreast, right, of the live video. Here, you keep abreast of the sensor data, the latest sensor data, of course, but you're also processing it to look for patterns of anomalies. That's the typical use case. So let's say the sensor data is reading certain, let's say it's reading the temperature, right, from within the factory, and your chemical process that's there in the manufacturing line is critically dependent on the temperature. If the temperature goes beyond a certain range because the climate is hot or whatever, right, you then have to shut down the processing line, shut down the chemical process because it can produce wrong results. If that's your kind of setup, if that's your kind of problem statement, then to be able to take action as the temperature changes so that you can automatically trigger a shutdown of the assembly line is something that requires continuous monitoring firstly, but also some kind of a thresholding function on the temperature. But imagine now it's not about a direct reading like a temperature, but imagine you are monitoring the health of a machine, and this machine is a critical machine in the assembly line, and if that machine fails, not only will the assembly line stop, but it consumes raw material. And when it consumes raw material, that raw material becomes waste if the machine fails in the middle of transforming the raw material. And let's say the raw material is extremely expensive, right? Like, for instance, diamonds, right? Or maybe one of the like nuclear power plants, as an example. So that kind of a setup, it's more important that you predict that something can go wrong and cut your losses, right? Prevent raw materials from being wasted, and therefore what you need to do there is collect the data, but also feed it into some kind of a unsupervised learning model or a anomaly detection model or any such models, right? Which can predict that and say that, look, something's wrong, you better take some action on top of it, right? You shut the line, stop the losses. Then the last of the examples here maybe involves some bit of human interaction, maybe it's automated, but it involves basically like a back and forth in interactive latencies. So this is different from the previous examples, which are all completely machine to machine typically. Here, it's a human that's sitting in front of a computer, interacting with you as a business, and as part of the business interaction, they are wanting certain information. Like, for instance, I'm purchasing a shoe on Flipkart as an example, and I'm about to make a decision, but I suddenly start to have a doubt whether the size of the shoe will fit me, and I need some help. Right? In that kind of a setup, if I've added the shoe to my cart, I'm about to say, this is my shipping address, and I'm about to enter the payment information. That's when it struck me, I should probably figure out the size match. So at that time, if you have access to a human or an expert, could be a bot, right? Could be a robotic agent as well. But some expertise that's available for you to reassure you that, look, you're making the right decision, helps in converting that transaction. And the opposite is also true, which is if you don't get the help at that stage, you're already in doubt, right? You're already not certain that you're going to buy this and this is going to fit you. And if you're not getting the help at that stage, you've potentially moved on and you're going to shop somewhere else. Like for instance, you're going to go to a physical shop, shoe store and try it out and things like that. So then in which case, the business that was online, which is Flipkart in this example, has lost you as a customer. And that's far more detrimental to the company than having a person who is always available for you to talk to as an expert. So if that's the case, how does that expert, let's say it's human-led, how does that expert know that you are the one that's actually looking at a shoe and not somebody else, right? That is actually a streaming data use case again, meaning the data that's being looked at from a website or from your mobile application gets continuously collected. As it gets continuously collected, there are these signals which are getting generated using machine learning, which say, is this person going to buy or not? Is this person likely to buy? Is this person likely to, do window shopping? All kinds of indicators like that, right? And the moment certain indicators go on, meaning that the indicators are turned on and the machine thinks that, yeah, there is a likely intervention that's required, then at that stage, automatically there is an SMS that goes out or a phone call that gets made. Let's say, hey, we see that you're actually waiting for something. Do you need some clarifications? Right? And that kind of an intervention from a human or from an automation system and resulting in some kind of an expert interacting with a customer in real time allows for the decision to be made positively. Now, the key point here is it's not a machine talking to a machine as much as it's a human potentially talking to a human, but the human to talk to the human is triggered by a machine which continuously monitors the signals, right? So it's a very good example, very practical example of streaming. All right, so with that, I'll close this part of the video. In the next part, we'll start looking at the streaming problem statement itself in a bit more detail.